Okay, hello everyone. It's 10 a.m. in Finland, and welcome to our VTT 50 qubit quantum computer up and running event, if I would put it that way. My name is Erja Turunen. I'm Executive Vice President leading digital technologies at VTT. But first, I would like to tell you that the chat will be open all the time for your comments and questions. We'll try to answer some of those today and then also afterwards, but please use chat. Then I really hope you mute your microphones. There will be quite a lot of people online, so please keep the microphones muted during the presentations. This is our agenda, so I will keep a few opening words by myself, but then definitely the main focus here today is that we will hear three sort of use cases, how the 50 qubit quantum computer has been used. And VTT senior scientist Jukka is giving a presentation about the ammonia simulation, and then we have two companies' presentations, Quanscient, is Oskari Kerppo telling about solving fluid dynamics, and then from Algorithmiq we do have Matteo Rossi who is sharing their findings about the photochemistry research for cancer treatment. If we open our minds first a little bit for the research all over and science, so did you ever think that we could grow coffee in the lab in Finland, or we could make egg whites without chickens? We can solve energy challenges with small nuclear reactors, or we can scale quantum computer as we are talking today. All of that we actually do at VTT, and we have been creating actually hope through this research already for 80 years. Our role is to combine actually multidisciplinary research by bringing together actually companies, universities and other research organizations. And by that way, we try to create radical change and sustainable breakthroughs. We always try to think beyond the obvious when we unlock new solutions. And today we are talking about quantum computing, which is very exciting topic and in all our agendas. And now I'm happy to say that actually the first 50 qubit quantum computer is up and running, and it's possible to use in Europe. So the 50 qubit superconducting quantum computer, we call that VTT Q50. That is a joint development project where VTT and IQM has worked together, and we have both brought our sort of best competencies together to create this achievement. And this has been actually carried out as an innovative public procurement process, which is also actually new learning for us, and it has worked very well. So now the VTT Q50 quantum computer is now available both for commercial and research use. Unfortunately, co-CEO Jan Goetz from IQM couldn't join us today, but here is one sort of thoughts he think that how this has been helped him. And actually in the chat there will be link for the press release we have published from this, so you can also learn more from there. But all over, everything is about cooperation and working in the ecosystem when we want to achieve sort of new bold achievements. So the VTT Q50 that now provides new opportunities for industries and companies in the Finland and for European ecosystem. And we will learn today then what kind of benefits we can get already out, for example, for new algorithms for material modeling, simulation, optimizing different problems, and also how to bring artificial intelligence into all of this. We do also have in Finland actually LUMI, which is one of the fastest supercomputers in the world. This is Euro HPC funded project, as you probably all know, and not going now deeper to that one to the lack of time, but the message is that actually LUMI is connected to the quantum computer, actually two of those, both VTT Q5 and then Q50. So now that's also the hybrid connection is now then available both for companies and researchers. And the new features with LUMI AI Factory, which is the new European initiative, will then add even more computational power to LUMI, including also experimental quantum computing platform for quantum computing and AI workloads. And the 50 qubit computer from Finland is also linked to that one. So all over, actually, the working in the ecosystem is something that in Finland we are sort of, we have long history for that one. We have low barriers how companies, universities, research organizations, policymakers can work together. And within the quantum now, the Quantinova R&D hub is something which is also then bringing everyone together, both in the field of the quantum technology and also in the field of the microelectronics. And it's also seamlessly connected to the European network because it's actually linked to the quite many pilot lines, and also then there's collaboration with the design centers. All the pilot lines are hosted by VTT, but VTT is strongly called as a part of the Quantinova ecosystem. And then if we think the European perspective on the quantum technology, we feel that Europe can really lead the quantum race by investing in equipment, software, and applications of quantum technology. And this also sort of, it involves fostering knowledge in education, institutions, ICT firms, and businesses using quantum solutions. So Finland and Europe, we have to focus on developing quantum innovations and turning high-quality research into the commercial applications. And in the pursuit of achievements, advancements in quantum technology, the European Union benefits from sustainable, substantial public investments, exceptional expertise, and robust research capabilities. So that was sort of my short message at the beginning, but now it's time to start the fun part and really go and deep to the use cases. So really quantum computing is already here, it's up and running, and our first speaker will be Jukka Aho from VTT. Please welcome and join us. Thank you.
Hello everyone, and welcome from my side as well. This situation, this event. Today I'm here to talk about molecular simulations using quantum computers. Let's get started. But before we dive into the subject, I want to highlight why we want to do molecular simulation quantum computers rather than traditional supercomputers. So, what is the difference between these two functions? N to the power of 2 and 2 to the power of n. For small n, the functions look pretty much the same, but let's see what happens when n gets bigger. And here we start to see the difference. N to the power of 2 is a polynomial function, whereas 2 to the power of n is an exponential function. And let's say that even when n is 100, we already see that we get a very big number for the exponential function, having 31 digits. And let's try one more time when n is 1000. So here we are, and n to the power of 1000 is a huge number. It's a bigger number than there is atoms in the observable universe compared to the polynomial function. Then the thing is why we do this molecule simulations using quantum computers. So the problem is that accurate molecule simulations grows exponentially, and classical computing capacity grows polynomially. And this is a big challenge. However, there is this quantum computers, and also their computing capacity grows exponentially. And this is matching very well. And let's now go to the actual problem of these molecule simulations. So first, a little bit about this ammonia. I have 3 points here that I want to mention before we go to the actual results. So why do we want to simulate ammonia? So first of all, ammonia helps us to move towards carbon neutral economy. It is estimated that the ammonia production cost is about 2% of CO2 emissions globally. There is a way to produce green ammonia, but let's say that we have some challenges, and we go to those challenges next slide. My second point here is fertilizers. So about 80% of ammonia goes to agriculture. And finally, ammonia can be used in energy and fuel applications. So there is no carbon, so it's a carbon-free alternative, for example, marine engines. And then it also can help in storage and transport of energy, because ammonia doesn't require such a cold temperature to remain liquid. So how do we produce ammonia in practice? It can be produced in so-called Haber-Bosch process. But the problem with this process is that it's very energy intensive. It's requiring very high temperature and pressure. But nature is doing this in a different way. So there is a certain bacteria that can produce ammonia in a room temperature. And the key here is a process called nitrogenase. And there in that enzyme, there is this kind of tiny metal cluster called FIMO-Co. And if we can understand how this process is working, so how the reaction pathways are working, we could basically produce ammonia in room temperature. But unfortunately, these reaction mechanisms are so complicated that we cannot simulate them using classical computers at all. But this would be exactly that kind of problem that we could solve using a quantum computer. And before we go to the actual results, I talk about that what we actually do in quantum computer. So when we say that we are measuring something using quantum computer, simulating molecule, what we are actually doing, we are calculating its potential energy, given some certain atomic configuration. So in conceptual level, it's pretty much the same than measuring, for example, energy of a mass spring system. And this, when we are measuring the potential energy with different configurations, we get something called potential energy surface, or PES. And from here, we can then, by finding local minimas and maximas and curvatures, certain that kind of things, we can then determine pretty much everything about the molecule dynamics and so on. So we can estimate its reaction speeds and so this is the first thing what we can do with what we start to do when we are simulating, studying the molecule. And here we have the results. So here I have been calculating this potential energy surface of ammonia and comparing it to exact quantum solution. And by exact quantum solution, I mean a solution what I could achieve using a noiseless quantum computer. And what is very interesting here that after post-processing, we get the very, very accurate results. And that is only like 1 millihartz far away from the exact solution. So as a summary, I would say that First, we have exponential scaling, and then we have exponential computing capacity. So quantum computers match very well for molecular simulations. And we have been now studying using Q50 3 months for now, and we are already getting better results than we are expecting. And finally, work-class tools and work-class infrastructure enable work-class results. That's all. Thank you.
Hello, my name is Oskari Kerppo, and today I'm here representing Quanscient and presenting the use case demonstration we did together with VTT on the VTT quantum computer. Quanscient focuses on multi-physics simulations. So multi-physics is when you are simultaneously modeling different coupled physical phenomena. So examples would be, for example, fluids interacting with structures, perhaps wind interacting with a bridge, for example, or acoustics, so a vibrating structure generating sound, or perhaps the thermal and electromagnetic properties of electric components. So here are some key numbers with Quanscient. We are founded in 2021, headquarters based in Tampere, and we have a very diverse workforce of around 40 employees. So what are also some of the traditional bottlenecks in classical simulations? So it takes a long time to build simulations, and it is a very difficult problem to even model the actual physics behind the problem. And then it takes a lot of money to perform the simulations. You have to have hardware or some cloud resources, and it's typically very slow to from modeling your product until the product actually sees the market. So these are the things we are trying to make faster. And actually, with Quanscient also, this is our product. It is a cloud-based product where we can already speed up simulations significantly, so we can achieve large speed ups and scale up physical simulations, and this can be seamlessly integrated in your design workflow. And this is what is available today. In the future, we are looking to go beyond what is possible with classical resources and actually make the impossible possible with quantum computing. So going to the demo with VTT quantum computer, we did a fluid dynamics simulation on the actual quantum computer. So here we have the classical validation of the model. So it is some aerosol spreading here through space, and this was validated on the CSC Lumi supercomputer. So it's the exact simulation, or the representing the ideal simulation. And then on the VTT quantum computer, this was, to the best of my knowledge, the first end-to-end execution of a repeated to the advection diffusion equation here, end-to-end on a quantum computer. And this underscores the huge potential quantum computing has in this field, addressing realistic computational fluid dynamics applications. Here on the bottom left, you can see the ideal simulation of this configuration. On the middle, you can see the actual result we got from the quantum computer, and we can see it very closely matches the expected outcome. So right now, the emphasis is on improving these higher level algorithms and practical quantum middleware engineering. So research gains from this collaboration, we gained quite a bit of information. So first of all, we had to adapt our quantum lattice Boltzmann method circuits for the quantum chip. So we chose the best subset of qubits for this simulation, taking into account the connectivity in the physical hardware. We utilized latest noise mitigation methods here. So we used dynamical decoupling to protect the states of the idle qubits during the execution. And we looked at the noise calibration, the calibration data directly that we got from VTT. And we sort of looked at this with some reference circuits to extend the noise model and actually build a classical noise mitigation model to correct some errors. And we saw quite a bit of improvement in the actual data once we corrected for the errors. Here, what we are looking forward to building in the future, we have, or this is a joint project with Airbus, where we are actually extending the quantum lattice Boltzmann method to 3 coupled phenomena. So here we have velocity, temperature, and stream function, which are simulated around an airfoil. So this actually represents a true multiphysics simulation. Here you're simulating 66,000 lattice points with 23 qubits. And this highlights sort of the potential that quantum computing has in these simulations. So this, as we heard in the previous presentation, these resources typically scale exponentially. And here the quantum advantage, one of the advantages is that we can scale these simulations up by adding the number of qubits. So in principle, adding a single qubit allows you to double the amount of lattice points you can represent. And then the algorithm at the same time only scales logarithmically. So the algorithm scales very favorably, while the size of the problem can be grown exponentially. I think there was one slide missing, but I guess that's okay. So if you want to get in touch with us, here are our contact information, and please get in touch if you have any questions or got interested. Thank you.
Okay, hello. So I'm Matteo Rossi, CTO and one of the co-founders of Algorithmiq. Sorry? Yes. Okay, so I'm Matteo Rossi, CTO and one of the co-founders of Algorithmiq, and will present some results that we obtained on the VTT Q50 on photochemistry for cancer treatment. So before going into the details of this project, I will just briefly introduce Algorithmiq. So we are a quantum software company, and we're trying to develop software that makes quantum computers useful already today and now. And in particular, we're focusing on one area where we think quantum computers are really the potential to be disruptive, which is healthcare and life sciences. So the quantum chemistry that helps us develop cures to cure and prevent diseases. So we founded Algorithmiq in 2020 in Turku here in Finland, And since then, we have grown to around 40 plus employees, distributed around London, also Europe and US. We have a very, expert team with a lot of interdisciplinary skills, because the problems we are trying to tackle are very challenging. And we raised over $20 million in investments. And we've been partnering with many entities and collaborating with universities, hardware partners like IBM, of course, VTT, and also end users like Cleveland Clinic in the US. So also here there was a slide missing, which was but I will try to explain it anyway. So when we talk about quantum software, we mean a stack of different layers. So software for quantum computers needs to, of course, focus on the application side. In our case, for example, our quantum chemistry simulations. And here we have a product that we call Aurora. But then you also need to solve a lot of problems that are kind of lower level in the stack, because quantum computers are still early stage. They still have limited sizes, limited capabilities, and they also are affected by noise, which means that you need to really optimize your algorithms and your kind of underlying infrastructure software to maximize the output. And in this area, we have a platform that we call DQI, which stands for Digital Quantum Interface. So with this in mind, we have been working to find use cases for quantum computers. And one of these use cases that we're really excited about is from a collaboration with Cleveland Clinic, which is one of the largest hospitals in the US. And they have a very large R&D department. And they're interested in photodynamic therapy for cancer treatment. I will explain in a second what it means, but I'm just mentioning that this is, we are part of a kind of a grand challenge organized by the Wellcome Foundation to examine the potential of quantum computers in healthcare and life sciences, called Quantum for Bio. And we are one of the few teams that has advanced to phase 2, and we will have hopefully soon go to phase 3, which means we can test on hardware at large scale what we are in developing. The photodynamic therapy. So it's basically a way to treat cancer in a way that is localized and minimizes the side effects of the drug on the body, which is a typical problem, for example, with chemotherapy. So a patient gets a drug, which is called the photosensitizer. The drug is absorbed all over the body, but it's inactive, so it does nothing. So the way to activate this photosensitizer is to shine some light at a specific wavelength, a specific frequency, in the area where the tumor is focused. And this activates a chemical reaction in the drug, in the photosensitizer, which will produce some reactive oxygen. And this will kill the cell in which the drug is. And this way we can only target specific areas of the body, and this is why this is very, very appealing. Of course, this is very nice, say on paper, but studying and developing these drugs is very difficult, because either you do it in the lab, so you do a lot of experiments, trial and error, and this is of course costly and time consuming, or you try to use computational methods, so computational chemistry. But Jukka, just a few minutes ago, showed very clearly why this is very difficult. So we need very precise computations to get the drugs right. And with regular computers, we would need extremely large amounts of memory and compute power to obtain that. But quantum computers kind of naturally fit in this computational endeavor, because they can be quantum systems. They can represent the state of the molecule very precisely. So the idea is to use a quantum computer to prepare this like reference state for our candidate molecule, perform accurate measurements, and then do some post-processing on regular hardware. to obtain then the chemical properties of interest. For example, a typical example is you want to know what's the energy difference between the inactive and the active state of your photosensitizer, because that is telling you which frequency of light you need to use to activate it. So this is a very kind of nice program, but then of course, quantum computers these days have still limited capability. And that's why you need to really use all the software tricks and methods that you can find to squeeze all of the performance from the computers that you need. And this is what we tested on VTT Q50, so on the Finnish quantum computer. We checked one piece of this puzzle, which is the possibility to perform very accurate measurements on the quantum computer. So chemists want their quantities to be known with a very high precision. This is typically the order of 1 millihartry, as again Jukka was mentioning, and this I'm showing in this plot, like kind of the gray area is what you, sorry, the green area is what you would like to have. So in this plot, lower is better. And what I'm showing here is exactly the precision in estimating this energy difference between these two active and inactive states of the molecule. The raw data that comes from the VTT Q50 is above this precision, and this is perfectly normal because there is readout errors and other sources of noise. But when you put your software like DQI into the picture, we are able to bring this precision down to acceptable, or even much better than the acceptable precision. You see here there are different qubit numbers. This corresponds to different like active spaces for the molecule that we have considered. So the larger qubit numbers, the more accurate description of the molecule you can get. And somehow a nice finding is that with the improvements that we did also on our software, we were able to beat our own results on a IBM quantum computer. IBM is one of the largest manufacturers of quantum computers worldwide. So this was very, very, very exciting for us. And we are like now on the path to go to larger and larger sizes of this active space, reaching 50 qubits, which is a regime that is kind of already very hard to match with regular computers. And we also need to show that we can mitigate all sources of noise besides in the measurement. And an interesting aspect is that this comes with not just quantum computers alone, so we need high performance computing as well in the picture. And this is also where LUMI and the integration with LUMI is going to be very, very important for us. And that's it. I just wanted to mention that really to get quantum computers, state-of-the-art quantum computers, able to tackle relevant use cases in drug design and discovery, you really need advanced software. And this is what we are trying to achieve here at Algorithmiq. Thank you.
Okay, thank you, Matteo, and thank you all. So we are actually all here still. If there are any questions in the chat. But first of all, then how to get access now to the VTT Q50? Here is actually a QR code and also the link to the website, so you can have more look from there. And really now it's best time to start. So sooner we start to learning how to work also in the algorithm side, the more we can achieve. And I just have to say, while my own personal background is actually in material science, I'm so excited right now. So what is all possible, we really don't know, but we hear already very good sort of concrete use cases. So what I want to still say that really quantum computing is here and now, and while we have actually International Year of Quantum Science and Technology this year, so let's really work hard and enjoy all the achievements. But currently there are no any questions in the chat, and so I think then it's time for us now then to actually close this event. thank you very much for all of you for participating, and you know from where to reach us and the companies. So please contact and let's continue cooperation together, and let's really create Europe as the leading place for quantum computing. Thank you and bye.